Hello, in this video I'd like to outline my approach towards studying the non-standard models of the weak monadic second-order theory of one successor. Recall that the weak monadic second-order theory of one successor is the first-order logic of a two-typed structure that has both a type for natural numbers, so we can have variables and expressions that represent natural numbers, and we can also have variables and expressions that represent finite sets of natural numbers. This is kind of like the script P for power set, except it's an F for the finite subsets, as opposed to all of the subsets of the natural numbers. And in our language, we can talk, of course, about containment. We can say that a particular natural number is within a particular set, and we also have a successor operation on the natural numbers. Recall that, generally speaking, a second-order theory allows you to talk about sets and relations and functions involving the kind of basic objects of your structure, but if we're restricting our attention to the monadic second-order theory, then we're only allowed to talk about sets of objects in our structure, as opposed to functions or relations. And then when I talk about the weak monadic second-order theory, here I'm saying that we're just looking at finite sets of the objects of the structure. One of the really important things about this structure was that we could describe less than in it. And we do this by talking about downwards closed sets. So we say that a set is downwards closed if whenever the successor of y is in X, then y is also in X. And we'll say that X is less than or equal to y if, for every downwards closed set, if it contains y, then it must also contain X. So again, it makes no difference if we consider the base structure of this thing to be the natural numbers with successor or the natural numbers with less than or equal to. Because once we have the second order stuff, we can talk about less than or equal to using just successor, and we can also talk about successor. We can talk about successor in terms of less than or equal to even without using the second order stuff. And so just like Pressburger arithmetic, this structure here is an extension of the natural numbers as a linear ordering. And so we're going to get the same situation. These structures here are going to wind up being woozles. There might be a restriction on what kinds of woozles we could be looking at. And then, of course, there's extra structure. In the case of Pressburger arithmetic, it was addition. And in this case, we have our kind of second order stuff, right? The ability to talk about finite sets. So there's two important considerations that we have to make when we're talking about non-standard models. The first is, can we construct any non-standard models? And then the second is, what do all non-standard models look like? Remember that with the natural numbers as a linear ordering, all of our non-standard models were isomorphic to a woozle of some sort. And all woozles were non-standard models of the natural numbers as a linear ordering. And so there we had a very precise and complete classification of the non-standard models. And so we could want the same sort of thing for our non-standard models of weak S1S. Specifically, we could want some collection where every non-standard model is isomorphic to one of the things in that collection. This is really convenient because it gives us a concrete way of renaming our elements of our structure to get some sort of intuition about the way that they're related to each other. Again, just like what happened in the woozle case. So let's say that we have some non-standard model of this structure here. The compactness theorem gives us tons of non-standard models of this particular structure, and in fact pretty much any infinite structure. And initially, there's not much that we can say about this structure. It's going to have a collection of objects of the first type and a collection of objects of the second type, and these can be arbitrary collections. All that we're requiring is that this structure here satisfies the same set of formulas as this structure here, and renaming the elements doesn't change the formulas, the logical formulas that are satisfied. So A and B can be just random collections that have random things in them. And this structure also is going to potentially have its own notion of containment, just an arbitrary relation between elements of A and elements of B. And again, all we're going to know is that this relation here behaves logically like containment does in this structure. And we're also going to have a notion of successor, and it's going to behave logically like successor on this structure, but who knows how it behaves on the set A. And so our goal is to rename the elements of this general non-standard model that we got in order to make more sense of what's going on in this structure. So to start off with, because A is a woozle with respect to this notion of ordering, we can rename the elements of A to be the elements of a woozle. We select some collection of elements that are infinite and infinitely far apart from each other, index them by a linear ordering, and then we have A is just natural numbers and elements of the form ci plus z, where z is some integer. Now there are some people who might say that our original model was a weak monadic second-order theory, and so our non-standard model should also be a weak monadic second-order theory. That is, that this second type here should be the set of all finite subsets of objects of the first type. And containment should be actual containment. There's a slight problem with that, though. If we make that requirement and make the requirement that this structure satisfy all of the same logical properties as this structure, then this structure actually has to be this structure. Specifically, in this structure, we can write down a formula that says for every element of the first type, we can talk about the set of elements that are less than or equal to it. That's going to be a collection of the second type. It's going to be a finite set. The set of all things less than a particular natural number is a finite collection. On the other hand, within this structure, if we're looking at some sort of woozle that's non-standard, then in order to get this structure to satisfy all of the same formulas, there's going to have to be a set in our collection that corresponds to the set of all things that are less than C. It's going to have to contain all of these elements. And that's an infinite set. And so if we're requiring B to be the set of all finite subsets of A, then A can't have any non-standard elements in it. A has to be just the natural numbers, and so B has to be the set of all finite subsets of the natural numbers, and now we're back at this original structure. There are no non-standard models if we make that requirement. And this is why some people will say that there are no non-standard second-order structures. There's a similar argument in the case, so this is kind of the argument that you can do in the case of weak monadic second-order theories, but there's also an argument that you can make in terms of just full monadic second-order theories. And so you'll hear people say that you don't get second-order non-standard models. But that's kind of boring, and so I want to drop the requirement that this B here be the set of finite subsets of A. I'm going to allow B to be anything, and just require that this structure here satisfy all of the same logical formulas as this structure here. That's why I want to think of weak S1S as a first-order logic of a two-typed structure. But now we're kind of in the reverse problem. We're letting B be anything, and this notion of containment be anything, as long as it satisfies the same logical properties as containment does in this structure here. And so one might ask, can we do this same renaming trick in order to rename the elements of this structure to be something sensible, so that we can get a good intuition for the relationship between the elements of this structure? Just like we did with A, just like we did with our woozles. Let me take a moment to draw out what this structure is going to look like. We know that A is some woozle. We don't know what B is. Containment is just an arbitrary relation between them. Successor is the actual successor operation on the woozle, right? We know how to take elements of the structure here and add one to them. So this structure is going to look something like this. I'm going to leave out the non-standard elements of A. They're there. I just want to leave them out on this diagram for clarity. The elements of B, I'm just going to indicate with dots. We haven't figured out what we want to call them yet. And the elements of A are going to be related to elements of B according to this relation here. So let me draw in some arrows representing potential relationships between elements of A and elements of B. So I've drawn these arrows fairly randomly because since we haven't given B any sort of internal structure yet, we don't really know how the elements of A are going to be related to the elements of B. But there's actually a pretty concrete way of renaming the elements of B to make sense of this relationship. And that's simply to name the elements of B the set of things in A that are related to them. So this element here isn't related to anything in A, so we'll call it the empty set. And again, because this relation is supposed to be behaving like containment, that really makes sense as a name for this set. This set here is related to 0 and 1, so we're going to name it the set containing 0 and 1. And so on and so forth. One of the things we have to be very careful of is that we haven't accidentally given two elements of B the same name. If our goal is to rename the elements of B, then this renaming operation has to be undoable. We can't have two elements start out different and wind up the same as part of this renaming process. So that would look something like this. And initially, if we're allowing B to be an arbitrary collection and this containment acting operation be an arbitrary relation, there's nothing stopping this from happening. It's only because this structure here has to be a non-standard model of this structure here that we wind up preventing this from happening. Because this structure is a non-standard model of this, and this structure here satisfies extensionality, this structure must also satisfy extensionality. Extensionality says that if we have two sets that agree on all of their elements, then they have to be equal to each other. And that prevents this sort of situation from happening. As such, it's perfectly fine to do this renaming of the elements of B to the set of elements of A that they're related to. This containment operation, when we do this renaming, becomes actual containment. And B is some collection of sets of elements of A. This leaves us with two questions. The first is, what sorts of woozles can we actually have here? In the case of Pressburger arithmetic, the types of woozles we could be looking at were very limited. But it will actually turn out that we don't have such limitations in the case of weak S1S. Any woozle can be the first order part of a non-standard model of weak S1S. And I'll prove that in a future video by constructing a very nice non-standard model whose first order part is an arbitrary woozle. The second question is, what could B be? What kinds of sets of collections of elements of A could be the second order part of this non-standard structure so that it still behaves like this structure here? This is a much trickier question. In this video, I'll talk about some of the basic set-theoretic operations that B has to be closed under. And in future videos, I'll talk about some more complicated operations that B has to be closed under. So let's talk about some of the basic sets that are going to have to be in B, and some of the basic closure properties that B is going to have to be closed under. So first of all, we know that B is going to have to contain the empty set. The standard model of weak S1S satisfies that there exists an X, there exists a finite set of natural numbers, specifically the empty set, such that for any Y, Y is not in X. And so this non-standard model is also going to have to satisfy this. Similarly, our standard model has a singleton property, and because we can express that singleton property as a first-order logical sentence, we know that our non-standard model is also going to have that singleton property. For any first-order object, there exists a second-order object that only contains that object. And that's going to be our general approach, identifying properties that our standard model has that we can also write down in first-order logic, and therefore our non-standard model is going to have. We also require that B is closed under some basic Boolean operations: union, intersection, and set subtraction. Again, the set of finite sets of natural numbers is closed under these things, and we can express these closure properties as first-order logical formulas. Because B has to contain the singletons and be closed under unions, and this is finite unions here, this isn't infinite unions, we know that B has to contain all of the finite sets. But we've seen that B also has to contain a little bit more, and I'll talk about that in a moment. We can also combine these properties to say that B has to be closed under finite modifications. If we have a set and we want to add a finite number of elements and then take away a finite number of elements, we're still going to have a set within B. And of course, we can add those finitely many elements by just unioning with the appropriate singletons one by one, and we can subtract off the elements that we want to remove by set subtracting the appropriate singletons one by one. As one might expect from the fact that WS1S is expressively equivalent to the regular languages, one can define in WS1S modular arithmetic. Here, if I have two concrete natural numbers r and m with r less than m, I'm going to say that an element of our model is congruent to r mod m if, for any set y, if x is in that set and that set is closed under subtracting m, then the remainder r is also in the set y. By being a little bit tricky about whether r is less than or greater than x, we can modify this definition to allow r to also be an arbitrary element of our structure, and so talk about whether two elements of our structure have the same remainder modulo m. But it's very important that our m be a concrete natural number, because here in the definition I'm talking about z plus m. And the only way to talk about that is if we apply the successor operation to z m times. That's only something we can do if m is a concrete natural number and not just some arbitrary element of our model that might be non-standard. Once we have this notation, we can write out various key properties of modular arithmetic. For instance, we can talk about any sort of remainder consistency facts. For instance, if x is congruent to 0 mod 4, then x must also necessarily be congruent to 0 mod 2. Since we can express these sorts of facts in first-order logic, they're also going to have to be true of our non-standard models. The remainders of non-standardly large elements are also going to have these consistency properties enforced on them, just like they did in Pressburger arithmetic. Another key fact is that 1 out of every m numbers is congruent to r mod m. Because m is a concrete natural number, we can write out this formula, replacing these additions with the appropriate number of successor operations and replacing this modular arithmetic notation with its definition to turn this into a first-order logical formula that expresses a true fact about our standard model and therefore expresses a true fact about our non-standard model. When we're looking at non-standard elements of our non-standard models, it's still going to have to be the case that 1 out of every m elements is congruent to r mod m. And in fact, the Boolean logic on this is a little bit gross, but we can express in Boolean logic that exactly one of these formulas is true. And as such, exactly 1 out of every consecutive m elements has to be congruent to r mod m. Just as was the case in Pressburger arithmetic, when we introduce a new element c using a compactness argument, we can choose the remainders of that c to be whatever we want, as long as they're finitely consistent. That is, they don't contain glaring inconsistencies like this. But again, we don't have any infinite consistency properties. We can have a number that's congruent to 0 mod all of the powers of 2, but congruent to 1 mod 3, and that's perfectly fine in this model as well. Every finite subset of these constraints is satisfiable, and so therefore the whole thing is satisfiable by some non-standard model. And again, just like in the case of Pressburger arithmetic, once we decide the remainders for an element c, that determines the remainders for all elements of the form c plus z, where z is an integer. Once we know that c is even, we know that c plus 3 is odd. But unlike in the case of Pressburger arithmetic, the integer parts of our woozle are completely unrelated to each other. Right? In Pressburger arithmetic, we had one integer part that contained c and another integer part that contained c plus c, and the remainders of c and the remainders of c plus c determined each other. Once we knew the remainders of c, we knew the remainders of c plus c, and once we knew the remainders of c plus c, we knew the remainders of c. This sort of situation doesn't happen in weak S1S. If we have separate integer parts, they can have completely different notions of remainders. They're completely independent from each other. It's a bit like if we were constructing a non-standard model of Pressburger arithmetic and we added in two new elements, c and d, we would be free to specify the remainders of c and the remainders of d, and they could be completely independent from each other. Similarly, when we add in new elements c and d to our non-standard model of weak S1S, we're going to get something that looks like this, and the remainders of c and d can be completely independent of each other. Once we have the ability to talk about modular remainders in weak S1S, we can talk about periodic patterns on particular intervals within weak S1S. This formula here describes the existence of a set which, on the interval from x to y, contains exactly those elements which are congruent to R mod m. And because we can describe the existence of these sets, and they exist in the standard model for any x and any y and any concrete remainders and moduli that we want, then we know that these elements have to exist in our non-standard models as well for any potentially non-standard elements, x and y. We could also, if we wanted to, specify more complicated periodic behavior by adding in more remainders. Let's take a look at a concrete example. We can construct, for instance, a set on the interval from the number 3 to the number, let's say, c1 minus 1, that contains all of the elements that are congruent to 1 mod 2. So that'll contain, I'll use 1 to indicate that an element is contained and a 0 to indicate that an element is not contained, 3, 5, 7, 9, and so on and so forth. And then this interval here contains this entire piece. We need to know how modular arithmetic mod 2 works on this piece here. Let's say for simplicity that C0 is congruent to 0 mod 2. Then this set will contain C0 minus 3, C0 minus 1, C0 plus 1, C0 plus 3, and so on and so forth. And then let's say that C1 is congruent to 1 mod 2, in which case this set is not going to contain C1 minus 1, but it is going to contain C1 minus 2 and C1 minus 4 and so on and so forth. And then it's not going to contain any of these elements past here. It's important to note that when we're talking about sets in these non-standard models, there has to be a largest element. And again, once we've determined what the first order part looks like and what the remainders within these various non-standard pieces of the first order part look like, this set must exist in our non-standard model. It must be in B, because in our standard model, for any interval, we can talk about the set of elements in that interval that are congruent to 1 mod 2. We can then combine intervals like this and then finite modifications, which is really just specifying the behavior on an interval of length 1 to produce arbitrary piecewise periodic sets. Here, when I'm talking about piecewise periodic sets, I mean that there are finitely many pieces. They're all intervals between one element and another element. They should be disjoint. If you want to overlap intervals, that really divides everything up into 3 intervals, and you specify the behavior separately on each of those intervals. Note that these pieces are going to necessarily have an upper bound, because there's only finitely many of them, and one of the pieces is the largest piece, and its upper bound is the upper bound for the entire set. And then we have periodic behavior on each of those pieces determined by the remainders, which we determined when we determined the remainders of kind of a base element in each of these integer parts. So this gives us a wide variety of sets that have to be in B. And remarkably, I'll show this in a future video, this is actually enough. B only has to contain sets of this form. It could contain more, in which case it's going to have more advanced closure properties, but this is actually enough. I'd like to take a moment to talk about a really interesting distinction between modular arithmetic in Pressburger arithmetic and modular arithmetic in weak S1S. In arithmetic, we can talk about whether a number is even or odd by talking about whether there exists an x such that x plus x is that number, or x plus 1 is that number. This naturally gives us a way of talking about our number halved and then potentially rounded down. In weak S1S, on the other hand, we're talking about sets that are closed under subtracting 2. Essentially sets that look like this, except we also need to toss this element in here. Once we see this set here, it tells us that all of the elements of this set are congruent to 1 mod 2. And the thing is, because we can't talk about C0 divided by 2, there doesn't have to be an integer part between this part here and this part here of our woozle, like there had to be in our non-standard models of Pressburger arithmetic. Again, you have to do a little bit of work to show that there isn't some other reason why we have to have a piece in here, but I'll do that when I show that for any woozle, we can construct a non-standard model that has that woozle as its first order part. For now, though, I'll remind you that we can't talk about doubling and we can't talk about halving in weak S1S, specifically because if we could talk about pairs of the form x comma 2x in weak S1S, we would actually have an undecidable theory. This is something that I showed in my undecidable extensions video a while back. And so, because the theory of weak S1S is decidable, right, we just take a question that we have and we can translate any logical formula into a corresponding finite state automaton, and so really we have questions about finite state automata which are easy to answer. Because of that, because weak S1S is decidable, it can't talk about doubling, and it also can't talk about halving. I also want to note an important principle involving these gaps here, these jumps from one part of our woozle to another. Let's say that we had these two separate sets in our non-standard model. I'll call the first one P and I'll call the second one Q. P is going to be the set of all odd natural numbers, a union together with numbers of the form C minus an odd natural number, and Q is going to be the set of all odd natural numbers, union together with the set of all C minus an even natural number. Initially, it might not seem that bad to try to put both of these sets into our non-standard model. Certainly, one of these two sets has to be in our non-standard model because it's, the periodic set between 0 and C0. And depending on our choices for the remainders of C0, we could have either one of these as a set within our model. But it turns out that these two sets are incompatible with each other. If one of them is in B, then the other one can't be in B. Remember that B has to be closed under intersection. And if we take the intersection of these two sets, it's going to be just the set of odd natural numbers, which doesn't have a largest element. And again, all sets in our model have to have a largest element. This is a very important principle I like to call the gap principle. Intuitively, it's that our non-standard model, because our non-standard model has to think that it's the standard model, right? In terms of the logical properties that it satisfies, it has to agree with the standard model. So as far as it can tell, it has to be the standard model. And in the standard model, we don't have these gaps. So it has to be the case that we can't talk about these gaps in our logic. And if we had both P and Q in our structure, we could talk about the place where P and Q agree versus the place where P and Q disagree. That would be a way of talking about this split here. Concretely, this means that if two sets agree infinitely on, let's say, the standard natural numbers, then they also have to agree up to a certain point into the next infinite bit that shows up. The point where the sets stop agreeing with each other can't be this infinite gap, because that would allow our model to see that infinite gap. Similarly, we can't have two sets that agree coming out of a gap if they don't also agree down to a certain point. Because again, our model can talk about this is the bit where Q and R disagree, this is the bit where Q and R agree, and that would allow it to talk about this split here, which again isn't in the standard model. And so these two sets are also mutually exclusive. Although we kind of knew that already, because if R is in our model, then P is just the interval from 0 to C0 minus R. And so if R is in our model, then P has to be in our model. And similarly, if P is in our model, then R has to be in our model. So the fact that P and Q are mutually exclusive implies that Q and R are mutually exclusive. So this puts us into a really tricky situation where not only does B have to be closed under certain operations, it has to be unclosed under certain operations. Certain sets in the structure prohibit other sets from being in the structure. And so it's actually not clear at this point if there's any consistent way of constructing a non-standard model of weak S1S. Again, you'll have to wait until a future video where I construct some concrete non-standard models of weak S1S. So let me take a moment to outline the plans for the next handful of videos. I'm going to want to be able to construct a whole bunch of non-standard models in order to be able to argue about what sorts of things we can and cannot say in this particular logic. With my first goal being to construct non-standard models whose first-order parts are arbitrary woozles. But in order to do that, I'm first going to need an axiomatization of weak S1S. Technically, you can do these sorts of arguments without them. We, for instance, proved that all of the woozles are non-standard models of the natural numbers as a linear ordering without resorting to an axiomatization. But in this case, it's just going to be easiest to construct our axiomatization first. Part of that axiomatization and part of our study of the non-standard models of weak S1S is we're going to want to know what sorts of operations is B closed under. We saw in this video that B has to be closed under some basic set-theoretic operations, finite modifications, and it also has to have a bunch of piecewise periodic elements. But our language is capable of describing finite state automata. So does that mean that there's more complicated things that we can describe using finite state automata that B is also going to have to be closed under? In order to study what functions on sets B has to be closed under, I'm going to want to be able to talk about what sorts of functions we can talk about in this logic. What sorts of functions can we talk about with finite state automata? And that means I'm going to have to talk a little bit about the regular functions. As part of this, I'm going to look at the Krohn-Rhodes theorem, which provides part of a generating set for the functions that we can talk about with finite state automata. And of course, if B is closed under all of the functions in the generating set, then it has to be closed under all of the functions that can be generated from them. I'm also going to want to take a look at some of the other things that we can do with B. I won't have a complete classification of the non-standard models of weak S1S, but I will have a lot to say about them, and I will be able to show you a lot of interesting things that wind up happening when we study these non-standard models. It really feels like, to me at least, that the non-standard models of weak S1S are just at the right level of complexity. When we were talking about non-standard models of the natural numbers with successor or the natural numbers as a linear ordering, those were really simple, and we could really quickly work out what all of the non-standard models were and everything that we could say about them. On the other hand, if we're talking about non-standard models of full arithmetic, the natural numbers with addition and multiplication, it becomes very tricky to talk about them. The structure is just too complicated because it can talk about the operation of Turing machines. But in my opinion, weak S1S falls right in the middle. It's complicated enough that there are some really interesting patterns that wind up showing up. We already saw that the interesting patterns that showed up with the Chinese remainder theorem for Pressburger arithmetic also show up in the case of weak S1S. But weak S1S is not so complicated that it becomes unwieldy to study the non-standard models. So let me know if you have any questions or comments down below, and I hope to see you in a future video.